everybody. Jesse here. We're going to do our 161 lab on density. It's going to be really quick because I'm only really taking maybe a couple of measurements. Normally what we would do is every person in the class would measure their Teflon ball. Since everybody's different and maybe does things slightly different or are using slightly different equipment, you might get slightly different data. And then we would take that data and run it through statistical analysis, and the statistical analysis will save us for being slightly bad scientists. So since it's going to be so short, I thought maybe what I should do is include some calculation portion for the video. This is something I do for my students when I teach this lab in person, because we're kicking off 161, and although we're teaching you chemistry, again, we are also kind of teaching you how to science in general. And since we're starting things off at that ground level, we want to make sure you're up to speed with some of your basic algebra and mathematics. So in this lab, these keep going off screen. These little balls, they're made of Teflon. So Teflon is a polymer, and the chains of the polymer, well, okay, I'm probably confusing you with a lot of sciencey words. All the polymer is some sort of molecule that we can take one subunit and make a long chain of them and repeat. We can make it as long or as short as we want, ideally. So Teflon, it's a fluorocarbon. You might be familiar with hydrocarbons. Let's say propane, meth, F, pro. These, of course, are carbons at the end. And since carbon can have up to 4 bonds, you would maybe, draw it out like this. This doesn't show the 3D nature of the molecule, but we're getting some hydrogens. So propane is a very simple hydrocarbon. Well, it's going to be a carbon chain, and then we're going to saturate that chain with as many hydrogens as possible. So we have a CH3, a CH2, a CH3. In organic chemistry, you would omit the hydrogens, and every corner is a carbon, and that's how we would draw propane in organic chemistry. So with that said, a fluorocarbon is the same thing going on with the carbon chain, except it's going to be fluorine atoms. So let's say we have our carbon, and I'm not going to draw the zigzag backbone nature. Let's say, so since carbons can only have up to 4 bonds, if they're single sigma bonds, we're going to saturate it with fluorines instead, right? And you can see this is just some sort of repeating thing. So we can say this little subunit is going to be our monomer, and we can repeat it n number of times and have a long chain, a short chain. And so it's Teflon. It's what's on your frying pans. It's utilized for many things. And these fluorine atoms, they're very electronegative, so they're bringing a lot of the electron density away from the carbon, and you're going to have this kind of bubbly electron cloud, and any other type of matter is going to have its own electron cloud, and they're going to repel each other. That's why Teflon is a good anti-stick coating. And so the reason why this might be good for us to have these pellets made of Teflon for measuring their density, well, we're going to use water. We don't want water to stick to the surface. We don't want water to be absorbed into the item, into the particle. Otherwise, it might throw off our measurements. So, with that said, and you might say, well, how can it be a ball if it's one long chain? Well, this long chain can wrap around a bunch of times. Think of spaghetti clumped together, and then your secondary van der Waals forces, will keep that chain kind of compressed, and you can form them into different shapes and such. So that's kind of the idea of what we're doing. However, we care a little bit more about the calculations right now. So the first one we're going to do, just to kind of get you back into the mathematics. So your biggest tool in Gen Chem, or maybe science altogether, is dimensional analysis. Dimensional analysis is just converting some item in some units and expressing that same thing, maybe in different units. So think of it as a machine, and if you just set it up right, it does all the work for you. It does all of your calculations. So one exercise I love doing, it's hot dogs to the moon. So there's some distance that we would express that the moon is away from Earth. There's certain times of the year the moon's a little closer, certain times of the year it's a little further, just like the sun and the Earth. But we have an average distance. So that average distance is 238,900 miles. And units are so important. In fact, the number is almost useless without the units. So I really care. When you guys are doing your homeworks, if you're in my lab or anything like that, I care more about the units, because if you don't have the units right, the answer is going to be completely wrong. So this is about 250,000 miles. Let's go ahead and be a little bit nice and express this in scientific notation. Here's another little trick. Let's say you want to express this in scientific notation. Put where your decimal is, right at the end, right? And I call these, it's kind of lame, I call these bunny hops. How many bunny hops do we have to do until we can express just the leading whole number by itself? So I'll write it out first. Okay, I'm going to express this as 2.389. We could round that, but just to keep the whole coefficient. Times 10 to some power. Well, what's the power going to be? Bunny hops tell us 1. See that? How I just go, I'm moving that decimal to the next digit over. 1, 2, 3, 4, 5 bunny hops. 5 bunny hops. So it's to the 5th power. And you see, I ended up putting that decimal with the bunny hops in. Similarly, you could, you can do this for numbers that are less than 1. Let's say you had 0.0003. Well, our decimal's right here. We're going to do 1, 2, 3, 4 bunny hops to make that 3 the leading coefficient with a decimal behind it. Not going to put a 0 because I only have one sig fig in that unit. Keep track of those. So 3 times 10 to, how many bunny hops did I do? 1, 2, 3, 4. But I went backwards, so it's to the negative 4. That's only going to help you. Scientific notation, it's maybe new, but it's your friend. It's so you're not writing out, 8 zeros after some number. And it makes our calculations a little bit more compact. And once you get into physics, you can do very basic, easy math with powers of 10, and it makes things much, much easier. So I'm going to go ahead and round this so we have a little bit more space. Sometimes what I do, since we have this tiny little white chalkboard and I can only write so much, maybe I'll put some unit factor and then some unit factor and then pretend that it's leading to the next one, but maybe I'll erase that board, and you can follow along and do this on a piece of paper. So we know our distance to the moon is some measurement of length. So we have 2.3, let's just round up and say 39 times 10, what did I say, to the 5th power miles. When you're doing dimensional analysis, you're telling a story. Your story is starting with something that somebody could hand you. I know it's abstract to think of me handing you 2.39 times 10 to the 5th miles, but imagine I took a tape measure and I measured it and I said, okay, here's the measurement. Maybe you're being handed some mass of something in grams. Maybe you're being handed some volume, but that's where our story starts. And so any number is equal to itself if you divide it by 1. It's not a big deal, but this is going to help us kind of keep track of things. We have a numerator and a denominator. So we need to get out of the unit of miles. And we know we're going to end up in hot dogs. That's going to be our final unit. So maybe what we could do is get out of miles, which is big, to something smaller. So we can go from miles to feet. Okay. And that is, I used to have this committed to memory. I had to Google a lot of these unit factors. There's no shame in that. Well, there is 5,280 feet in a mile. Okay. I call this the seesaw rule. If you saw it here, you should see it down here. Okay, so that's like a seesaw. See how it goes diagonal? Okay, dad jokes. Awesome. And you can see from this, you know, let's say you had a centimeter divided by centimeter. Well, it equals 1 because centimeters cancel out. And well, they both had a leading ninja 1. 1 divided by 1 is 1. So with that said, the miles cancel out. Now we're talking about feet. We're in feet land. We're in feet land. Okay. So again, pretend this calculation is continuing this way, but really I'm going to write the next part on this side of the board. Okay. So now that we're in feet, we're going to say, okay, well, feet, it's in the numerator. The next part should appear in the denominator. So easy, you know, for every 1 foot, we have 12 inches. You know, we want to keep expressing, if we're doing a conversion, we typically want to go to something smaller and smaller and see how many we end up with. Okay, well, again, feet canceled out. Now we're in inch land. Okay. All right. Now, for every 1 inch, feels like I'm just writing bigger and bigger with each one. We have 2.54 centimeters. Sorry, I'm not trying to talk at the board. So, now inches have canceled out. Now we're in centimeter land. So, usually I would stop at inches and say, well, okay, a hot dog's about 6 inches. Instead, I wanted to show you with more units how this plays out, you know, to make it a little bit more complicated to show you, you know, the nuance of these steps. And again, you know, you can do this along with the video on a piece of paper so you can see, it's really good to see all the unit conversions spread out, you know, end to end. I've had very long, complicated problems in analytical chemistry where you could go and make an ice table and then you could do this and do that. I was in the test, I solved the problem with one long logic of dimensional analysis and it got me the right answer. That's the power of this tool. So now that we're in centimeterville, so 15.24 centimeters are in 1 hot dog. Okay, so centimeters canceled out. Now I'm in hot dogs. I don't have any other unit that's going to appear in the denominator to cancel out hot dogs. You could even write an equal sign and know, okay, my final units need to be hot dogs. And you know, once you see that unit, you can circle it, you can stomp, you're done. You can punch it into your calculator and get an answer. So I went ahead and calculated this already before I gave this little talk. It turns out that there are 2.52 times 10 to the 9th hot dogs to get to the moon. If you stacked this many hot dogs end to end, they would reach the surface of the moon from Earth. That is, so magnitudes, power of 10. 10 to the 6th is 1 million. 10 to the 9th is 1 billion. So this is telling us you would need about 3 billion hot dogs to go from Earth to the moon. That should give you kind of an idea of the scale of the distance from the Earth to the moon. You could literally feed half the world 1 hot dog, or you could stack those hot dogs end to end and get to the moon. So that's kind of It's not just, to show you that you can do the calculation, but it's a good way to do some just basic calculations on molecules and atoms and atomic masses to give you an idea of how tiny these things are, how tiny these particles are in their interactions. They're so small, there is no wavelength of light to actually see them with the naked eye under a microscope. We have to use other means and methods to see what's going on with these things. So one more calculation. I heard anecdotally somewhere that if you took all the gold on Earth that has been mined and melted it down and you can make one cube out of it, you would end up with a cube. Oh, here's a nice little thing if you're going to do inorganic chemistry at some point. See these lines, how I drew them? I drew 2 lines, kind of some distance apart, the same length, same height, and then I drew 2 other lines slightly offset. See that? And then you can just connect the dots, and you end up with a nice cube. Okay, so let's say I had all the gold that has been mined. I could make a cube that each side was about 60 meters. So 60 cubic meters of gold. I don't know if this is correct or not. I remember just hearing this. And you could either have all the gold in the world in a big giant cube, or for about the same amount of money you could purchase all the farmland in the United States. And the idea is you would not want all this gold because it's just going to sit there. Maybe it appreciates in value. But all the farmland in the United States that you could buy at the same price will keep making food and keep making you profit. So I thought this was kind of an interesting thing, and it's a really good example of doing some dimensional analysis. So let's say you had 60 cubic meters of gold. I'll even put a unit, AU for gold. So here's where students make a lot of mistakes when they're dealing with cube things. A lot of students would write, okay, for every 1 meter, I have 100 centimeters. Boom, done. No, you're not. There's actually a little bit more going on here. So yeah, you would start off and say, okay, I have 1 meter. This is just me arbitrarily trying to convert from cubic meters to, let's see if I wanted to know how many grams of gold I had, or how much money that was worth. So yeah, for every 1 meter, you have 100 centimeters. See that? So I have my 1 down here. These are all fractions I'm lining up. Okay, well, see, this is meters to the cube. This is meters to the first. So when you have some power in the numerator and some power in the denominator, remember how they canceled out? Well, it's whatever this power is minus whatever this power is. I have some random stopwatch going off in the lab. Okay. So this would be 3 minus 1. So that would turn into a 2. And yeah, I cancel that meter out. Well, I still have 2 more meters I have to cancel. So I would do that another time. And then another time. And you see how to fully cancel out all those meters, I needed to go 100 centimeters times 100 centimeters times 100 centimeters. Or you could write to cancel out meters cubed and going into centimeters cubed. 1 meter, 100 centimeters. And then you cube everything. And by cubing everything, you're saying 100 cubed. It's 100 times 100 times 100. You're going centimeters cubed. You're going meters cubed. Then you ensure meters cancel out. And now you're talking about centimeters cubed. And you see the coefficient of 60 had to be multiplied by 100 times 100 times 100. Not just one time. And so it threw off our units, it threw off our coefficient if we didn't keep track of this. So now that we're talking about centimeters cubed, okay, let's say we know that, well, for every 1 cubic centimeter, hey, that's 1 milliliter. Okay, that's useful, right? So now we're talking about milliliters. Well, now we can implement in our calculation the density of gold. So I Googled this, word on the street, for every 1 milliliter, we have 19.3 grams. You know, if you're doing a density lab, you might think, oh, why is density important? It's very important. It's a very important measurable quality of materials. And we can use it to just kind of do our basic research and discovery and learn more about science. So 19.3 grams. So I took some measurement, 60 meters cubed. Well, now I know how many, I don't even have to put that thing on a scale and mass it. I know the mass of that cube now through doing this dimensional analysis. Again, cubic centimeters had canceled out before, milliliters canceled out. Well, now we're talking about grams. And so I could take this one step further. Again, feel free to follow along on a piece of paper as I'm doing these so you can see it all laid out. Well, I also Googled, well, for every, grams is in the numerator, so the next step it should go the denominator, seesaw rule. So for every 1 gram of gold, you could sell or buy, with US dollars, $62. So then you could say, well, I have this many grams of gold. How much money could I get if I were to sell all that? Right? Okay. And based on this calculation, it turns out if you had this theoretical giant cube of gold, well, you could either have 1.16 times 10 to the 9th grams. Okay, again, that's about 1 billion grams. Okay. If you were to sell that, you could make 7.18 times 10 to the 10 dollars. Right? Okay. To give you an idea, that's what, $70 billion. I would imagine that there's more gold on Earth than $70 billion worth. So maybe this theoretical cube would actually be bigger. If you could take all the gold on Earth that's been mined and collect it and melt it down and make one cube. Okay, so that should hopefully give you a little bit better idea of how to do these calculations. This is one of the biggest things you should be getting out of your Gen Chem. And since we can't be together in the lab, this I would already be showing to you in person. So hopefully, we're doing just as well with these videos. All right, looks like I got a little excited and ahead of myself. I wanted to show you something of the board before we take our measurements. So let's pretend this crude drawing is our graduated cylinder right here. So we're essentially looking at this, but blown up. And on this, we have, here's the 10 milliliter mark. Here's the 15 milliliter mark. And then between 10 and 15, I drew them off to the side here to accentuate, there is extra 1 milliliter marks. So we're at 10, 11, 12, 13, 14, 15. When you're using these and you're making your measurement with graduated cylinder, well, water is polar. Little chalk dust. And the glass is polar too. So water likes to stick with itself, right? But it's also going to try to stick with the glass. And so when you're looking at the fluid inside of the graduated cylinder, You can notice this in just about anything that has some sort of aqueous solution or water inside of something that's glass. And you can see it's creeping up the sides because it's attracted to it. It's literally trying to pull itself up out of the cylinder. And then gravity is at some sort of an apex where there's the absence of the glass. Well, that's the middle of the cylinder, where gravity is more effective at pulling it down, and there's no glass for the water to pull up. So you get what's called a meniscus. If this were mercury, liquid mercury at room temperature, you would actually have the opposite. You would have a bubble, right? Because the mercury is not attracted to the glass, and so it's trying to repel from the glass, but still have ionic bonds with itself. And so the way to measure this is you need to measure, see this curve? I'll even blow it up. Let's say this was our meniscus to kind of accentuate it. Well, here's the top of the curve, here's the bottom of the curve. You want to get kind of at eye level with that measurement. You don't want to look above it, you don't want to look below, you want to get eye level. And you're always measuring. I just can't do anything today. You're always measuring at the bottom of that meniscus, and that's how we would make our measurement. So in this case, we see, okay, our meniscus is about at the 11 milliliter mark, right? Okay, well, there's a little bit more to that. What you can't quite see, and I'll blow up here on the side, is we have the 11 milliliter mark right here, and then we have the 12 milliliter mark above it, above the meniscus. So there's that one. Okay? And so our meniscus lies somewhere in between these two. And we don't have a marking on the glass, but we can eyeball. We can look at it with our eyes. And so the way to do this, any kind of glassware or labware that you're using, and you have two markings, you're supposed to use your imagination and try to imagine 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You're supposed to partition it into 10 imaginary subunits. And then eyeball, well, okay, that is 11, I know it's 11 milliliters. 1, 2, 3, 11.3, right? Or you might even see in the lab book, you know, they gave an example where we had an extra decimal. They show for this in there. I'm just explaining a little bit more in depth. And you would see that we have, you know, in this measurement, okay, we technically have 4 sig figs. But know that we have uncertainty in this last digit. Or in this case, we have 3 sig figs. And our uncertainty lies in the 1/10 of a unit decimal place. So we can say, okay, it's 11.3 plus or minus 0.1. And you can follow along in your lab notebook how they do this and how it affects the math. A lot of students will look at this and they say, oh, it's 11 milliliters. There's a little bit more to it. You know, we need a little bit more precision and accuracy in our measurement when we're doing stuff in the lab. So, okay. Now we'll do the experiment, I promise. Okay, everybody. So first things first, we need to obtain a mass of our Teflon ball. We're just going to kind of utilize this view so you can see what I'm doing in the lab. So first things first is we always want to keep this weighing pan clean. You know, it's Hawaii. Even stainless steel rust, sometimes chemical spill. You know, we use these things, they get a little worse for wear. That's why you would always use some sort of medium between this and whatever you're trying to mass. You know, this simple weigh boat, you can use wax paper, you know, little plastic weigh boats, whatever you have in the lab. So the first thing is we would put our weigh boat on the scale. Well, it has a mass, you know, big surprise. Well, I guess I didn't make this where you can see. Okay, these are the controls. One thing you just really need to know is that we're gonna tare this mass. So it has some sort of mass, well, we're gonna negate it. we're going to just set it to a new 0. And you might notice that the mass is fluctuating. Well, part of that is because these scales, they do fluctuate. You can see we're getting to the last significant digit that this scale is capable of, and so it itself has its own uncertainty. And you could account for that where you would have these as all your sig figs, but that is the uncertainty digit. So plus or minus, 0.01 gram, or however we were going to do that. So we have our Teflon ball. I'm going to go and just put it on the weigh boat. Okay. And then just give it some time. Let it equilibrate. Again, we're under a vent, so we have this kind of wind pushing down, and it's not great, but it's not terrible. So we are going to go and write down our mass. And the thing to remember is you want to make sure you do all of your experiments with that same one Teflon ball that you massed. You wouldn't just mass this one and say, oh, they all are going to have this mass. In an ideal world, however, when we manufacture things, we find that that is not the case. Every big screen TV that you could buy in Costco is maybe going to have a slightly different dimension of the plastic casing for the outer frame. That's just the way the world is. Okay, so we have our mass. We'll go ahead and go over to our lab bench. All right, so it's a pretty simple experiment. All we really need is obviously a scale to get the mass, some sort of measuring device like a ruler. This is our graduated cylinder. This is a 25 milliliter graduated cylinder. I believe we have ones that are more precise, you know what I mean, where we would have more notches per unit of milliliter. However, we needed ones that would also fit inside, so we could actually submerge the Teflon ball. A little bit of DI water and a squirter, and then of course our Teflon balls. Here's the one I masked earlier. So maybe the first thing would be obtaining a diameter of the Teflon ball. So one thing I like to do when I'm taking a measurement of something that's round is I just like to hold it up against the ruler, and even though it's round, I just try to see how I can put one edge right on that 0, and I try to see at what oh boy, I try to steady the camera. I try to just see at what unit it eclipses. So I could say 3 centimeters is my new 0, right? So 4 would be 1, it's arbitrary however you do it. So I would try to just line it up to where with my line of sight, I'm right on that leading edge for the line of 3. And then I'm trying to see, well, it's really hard to do this looking into the phone. Okay, there we go, that's a little better. It's kind of hard to see from your vantage point because I'm holding it. But see how, okay, one edge is right on the 3. At what point does the sphere eclipse on the other side? Well, it looks to me like it goes to almost exactly 3 dashes, 1, 2, 3 dashes before the 5. So if that is my 0, it goes to 1, oh boy, my eyes suck. 1, 2, 3, it goes to there. So that would be what, 1.567, 1.7 centimeters. Now you notice how I said it was about exactly on the line? Well, remember what I said earlier about the measurements for any kind of line, whether it's a ruler or a graduated cylinder. So I said it was, diameter was 1.7, and I said it was on the line, so that's why I can justify saying 1.70 centimeters. And, they're not so keen on the uncertainty here in this little diagram thing. So we're not going to worry too much about the uncertainty. The other part of this is, let's say we have our sphere, right? Okay, that's our round object, yeah. Well, I just took a diameter, yeah.
that means I took whatever this length was from one end of the sphere to the other. Typically, when we do measurements with spheres and we're measuring volumes and areas, diameter is equal to 2 radii. Well, a radii is just from the center of the sphere to the outer edge. So you might, see in your mathematics how we have some sort of flat circle. We say this is the radius, yeah? Well, going around the circle halfway, imagine if you took this radius and then chopped it out and laid it flat against the curve. See that? You could lay it on the curve and bend this. How many of those could you fit around the circle? Well, halfway around a circle is 2 pi. Oh, I'm sorry. I am so sorry. Wow. I need my afternoon coffee. It is 1 pi radii. But if we went around the circle the whole time, that would be 2 pi radii. And then what is it? The area of a circle is pi r squared. And so your task is going to be Googling what the volume of a sphere is. And I can tell you, you will find some sort of expression of pi, some sort of expression of radii, and something squared. I'm really copying out, I can't think of it off the top of my head, but you can Google this, and then you can figure out what the volume of your Teflon ball is based on this diameter measurement. And well, just some quick algebra, well, your radius is 1/2 the diameter. So express that measurement we took, or the data sheet will be giving you, and express that diameter actually in radius. Look up the expression. This is not the equation, but it will involve pi and radius, and something will be squared, maybe even 4/3, I want to say. And plug it in, and then figure out what your volume of your sphere is in cubic centimeters. Well, a cubic centimeter is 1 milliliter, so that's kind of the meat and potatoes of what we're getting to here. So, to get to the actual experiment, I'm going to take our GI squirter. It was recommended, we fill it up to about 10 milliliters. You want it to be deep enough to where this thing can be completely submerged. And the other thing is you don't want too much of the water to stick to the sides when you're squirting it, because then later on in the experiment it can finally fall down, and it can affect our measurement. So I am going to try to put the neck of this a little deep in there. I'm going to squirt straight down until I can fill it up. Pretty simple, nothing too groundbreaking here. I'm going to take it all the way to about 15 milliliters. Now, here's the thing. A lot of you would be tempted to go drop for drop until it's right on the line at 15 centimeters. That's not actually what our goal is. In fact, maybe on purpose overshoot or undershoot to some arbitrary value. You can see I got a little bit on the sides there. It's not going to affect our measurement too much. And so I'm going to really quickly take the measurement myself, write it down, and then I'm going to try to show you with the camera what I am seeing. So I'm going to say 15 points. 15.5, I think. Yeah. I'm going to say my measurement. Now this is the initial volume of the water. So I thought it was 15.5 milliliters. And I'm going to see if I can show you really quick what I am looking at. Okay, so when I did my measurement, I got down here on one knee, and I got at eye level with this thing. And you can see the 15 mark, you see the 10 mark, you see the larger line that wraps around. It's kind of hard to see the background. Wow, and I can't do that with my left hand. Okay, we're having fun. All right, so there is the 15 mark. You see that line above it is the 16 milliliter mark? So what I'm doing here, it's really hard to see. See how I'm kind of in between those two? And I'm right at eye level and I'm measuring, you can see the curve of the meniscus. I'm measuring the bottom of the curve. And to me it looked like it was 15.5 milliliters, right? So that's our initial volume. Put this back into the self-stick. All right, so we have some initial reading. Now, I'm gonna put the Teflon ball in there and it's going to displace a certain amount of water and the water level is gonna rise and I'll have a new measurement. The better thing to do is to not splash this water because I don't wanna lose any from the vessel. I wanna maintain everything that's in there because it's only gonna make my measurements better. So I'm gonna slowly tip this, let it roll in. I don't think I lost too much. Okay, well, the Teflon ball went to the bottom, so that should tell us it's denser than water. And water has a density of about 1 gram per centimeter cubed. So I'm gonna take my next measurement. Well, to me, it looks like, oh, you know what? I'm just now realizing the spacing on this. I messed up on my last measurement. That mark that I showed you that I said was the 16 milliliter mark, it was actually the 15.5, which would mean that my first initial reading, you know, scientists mess up every day. It means that my initial reading was actually 15.25. Okay. And therefore, my uncertainty, I would argue my uncertainty was still plus or minus 0.1. I'm just saying 0.25 because it seemed in between those 2 points. You would maybe round this up to 15.3, right? And still say that uncertainty is plus or minus 1/10. So it has risen now, so I'm going to take that measurement. 1, 2, so that is 16, 17. Looks like it is now 17. I'm going to say 17.2. It looks like it's at 17.2 milliliters. Okay. And so we're just gonna, what we care about here is the delta of the water. Whenever we're taking a measurement, we don't actually measure what it is. We use some sort of device that will measure the delta. So real quick, I'm just gonna do some side math here. That was 17.2 minus 15.3, Okay, 7, 8, 9. Okay, so my delta told me that this was 1.9 milliliters that I displaced, and that the Teflon ball weighed 4.050 grams. Probably saw or will see in my Excel video, the reason chemists love density is because it is mass over volume. That makes a nice heart, and that equals density, and that is the Greek row for density. So you can literally take whatever your mass is and divide it by your volume, and you will get a density. In this case, it was 4.50 grams divided by, wow, I have a goldfish memory. I can't even remember two numbers for 5 seconds. 1.9 milliliters. And I'm not going to bother punching this into a calculator. That's not the point. I would get some number. And look here, my units would be in grams per milliliter or grams per cubic centimeter. And that's the important part, is that I obtain some sort of a density. Okay. And if I didn't know what these balls were made of and I wanted to find out, I could do this procedure and be like, oh, wow, you know, the density I obtained just so happens to be really close to Teflon. So I think this is Teflon. And real quick, I guess I'll show you my final measurement so you can see. You know, and the whole point of you doing Gen Chem, so sorry you can't be here in person, is, you know, it's really easy to misuse the equipment or not understand it, so it's really just practice for when you're going to do maybe a harder chem like Chem 2 or organic chemistry. So here's the mistake I made. This is a good teachable moment. See how I have this nice big fat line that wraps around the whole thing. Then I have this this line that's not that wide and then a slightly wider line above it. Well, that was 15, then 16. And so this in between was 15.5 milliliters, yeah? And so that's how, you know, we actually have 10 markings between 15 and 20. Well, there's only 5 milliliters between 15 and 20, so therefore some of those must be half marks. You should consider that if you were going to consider your uncertainty. Again, we have those two lines that indicate half a milliliter. Well, imagine it was split up into 10 pieces and you were going to eyeball some decimal point to determine your uncertainty. So that is pretty much the density lab in a nutshell. I believe what we're going to be doing is sending you a sheet of data from another lab. This was really just to show you how you would be doing this if you were in lab, and hopefully teaching you how this technique works, because eventually, you know, all this is going to be over and we're going to be doing labs and classes in person. We just want to make sure that you're up to speed enough so when you're doing a molecular biolab, you have the skills and knowledge and tools to, you know, do some cool experiments. All right, everybody, that kind of concludes everything. I hope you enjoyed this. Thanks.